In this video, we use a famous inequality called the Cauchy Schwarz inequality to complete the picture of a geometry on an arbitrary vector space with inner product. First, a few definitions. If V is a vector space with inner product, then we call V an inner product space. If, in addition, V is finite dimensional, then we call V a Euclidean space. So, a Euclidean space is an inner product space which is finite dimensional. Now, another important definition. Let V be an inner product space, an arbitrary inner product space, perhaps finite dimensional, perhaps not, and let U and V be two vectors in V. We define the length or the norm of a vector U in V using the inner product as follows. The magnitude or norm of a vector U is denoted with the same notation we saw for R2, R3, and Rn. Magnitude of U is the square root of the inner product of U with U. And again, I'll remind you that this should be, we should think of this as being motivated by the length of a vector in R2 and R3, which was just length of U equals U dot U. That was a formula that we stated back there. So that was true in R2 and R3. So the idea is that we're just generalizing this to give a notion of magnitude on an arbitrary inner product space. And the next geometric property we want to capture is the angle between two vectors. So in an arbitrary inner product space, let us attempt to define the angle between two vectors. Remember, in R2, we saw that the angle between two vectors U and V is given by cos theta equals U dot V over magnitude of U times magnitude of V. But of course, now we're in an arbitrary inner product space. This isn't R2 anymore, and we don't have the dot product anymore. We have an inner product instead. So let's try to replace the dot product with the inner product and attempt to define the angle between the two vectors as follows. Let's say the angle between two vectors U and V is cos theta equals inner product of U and V over magnitude of U times magnitude of V. After all, it worked well enough with the dot product. But there's a problem with this one. So this definition for magnitude works fine. That is the magnitude or norm of an arbitrary vector in an inner product space, finite dimensional or not. Everything works great. This one may not work because we have to remember that the range of cosine, remember the cosine function looks like this. The range of cosine is between -1 and 1. So this expression can only be solved for the angle theta if this thing on the right is a number between -1 and 1. But we have, so far, absolutely no control on the size of this and the size of this. So it is difficult, if not impossible, to tell whether this number over here may be bounded between -1 and 1, or may grow very large or very small. If it's some number outside of -1 and 1, say 5, 10, then this whole notion of the angle doesn't make any sense. So this whole conversation at this point is highly speculative, unless we can show that this quantity, which I keep circling, is between -1 and 1. And so that will be our goal now. Now we state the celebrated theorem, the Cauchy Schwarz inequality, which is named after two mathematicians, Augustin Louis Cauchy and Karl Hermann Schwarz. You should read your book. There's a short biography of these mathematicians and the contributions they made to mathematics, one of them being this important inequality, which we'll state now. Let V be an inner product space, and let U and V be vectors in V. Then the Cauchy Schwarz inequality says that if you take the inner product of U and V, and then you take the absolute value of that, it's less than or equal to, there's the inequality part, the magnitude of U times the magnitude of V. I state this inequality without proof in these videos, but I strongly encourage that you pause now or at your earliest convenience and go to the text and read the proof of this theorem. It's very interesting because the proof involves, it seems, very few properties of vector spaces. In fact, the proof invokes some properties about roots of a parabola in R2, which doesn't seem to have anything to do with vector spaces on its surface. So it's a strange proof that's used to prove the Cauchy Schwarz inequality. Let's get around to using it. For an example, let's take this vector space again of all real-valued continuous functions on the unit interval, and let's take as vectors the polynomials t plus 2 and 2t minus 3. Now, of course, these functions are defined on the entire real line, but we can consider them as elements of V by restricting their domain to the unit interval. So I would like to calculate three things. I want to calculate the inner product of these two vectors, and I want to calculate the magnitude of each one of them. So let's calculate the magnitudes first. Remember, in this more abstract vector space, our notion of magnitude is captured by the inner product via this definition. The magnitude is the square root of the inner product of U with itself. Remember, the inner product of two vectors is the definite integral of the product of the vectors on the interval from 0 to 1. So we take the square root of that. And if you calculate the value of this integral, we finally get square root of 19 over 3. So that's the magnitude of U. How about the magnitude of V? Using the same definition gives us the magnitude of V is square root of 13 over 3. Now let's calculate the inner product of U with V. So that will be the integral from 0 to 1 of the product of those two functions, t plus 2 times 2t minus 3. And I'll let you go ahead and calculate that on your own, and hopefully you will find that the answer is negative 29 over 6. And you can verify for yourself by plugging these numbers in that the absolute value of this inner product is indeed just barely less than the magnitude of U times the magnitude of V. Here I have absolute value of inner product is this, and here's magnitude of U, and here's magnitude of V. Put these numbers in, I think you get 4.83 rounding off on the left is less than or equal to, you get 5.2 something on the right. So the Cauchy Schwarz inequality is certainly maintained in this example. Here's the Cauchy Schwarz inequality written one more time. I want to do something special with it, something relatively simple. I just want to divide both sides by the magnitude of U and the magnitude of V. So if I do that, I obtain the following expression. The absolute value of the inner product of U and V divided by magnitude of U times magnitude of V is less than or equal to 1. Now, I can write this thing on the left-hand side as the absolute value of the entire fraction, since the denominator is always non-negative. And to say that the absolute value of a real number is less than 1 is to say that the number itself is between -1 and 1. That is, this entire expression is between -1 and 1. And this is because of the Cauchy Schwarz inequality. But what's the upshot here? What else is between -1 and 1? Cosine is between -1 and 1. So if this number is between -1 and 1, that means there exists some angle theta such that the cosine of theta is equal to this fraction inner product of U and V divided by magnitude of U times magnitude of V. This is precisely the obstruction that we were worried about before when we wanted to define the angle between two vectors. We couldn't quite do it because we weren't sure about the value of this expression. But now, because of the Cauchy Schwarz inequality, we know it's between -1 and 1. So we can define the angle between two arbitrary vectors in any inner product space. And now we can finally finish our picture of the geometry of an inner product space. And it looks like this. Let V be an inner product space. The geometry of V is described as follows. We define the magnitude or the norm of U as the square root of the inner product of U with itself. We've seen that already. And now we have the second piece of the puzzle. The angle between two arbitrary vectors U and V is given by cos theta equals inner product of U and V over the magnitude of U times the magnitude of V. We'll just do one brief example to conclude. Let's continue the example we saw above with V, the vector space of continuous real-valued functions, and we took two polynomials, t plus 2 and 2t minus 3. We found the magnitude of U and the magnitude of V, and we found the inner product as well, but now we can find the angle between these two functions. So, given our new definition for angle, we've already found, of course, these inner products and these norms, or these magnitudes, so I'll just borrow those figures from before. And we get -29/6 divided by root 19 over 3 times root of 13 over 3. So we should calculate this just to get a concrete number. And so I did that. I calculate the cosine of theta is -0.922, rounding off. And if I solve for theta, I get theta equals approximately 2.744, that's in radians, 2.74 radians. So that's the angle between these two vectors. And again, this has to be taken with, I guess, some framework of abstraction, because it is not as if we can draw these vectors U and V in any n-dimensional Euclidean space.